Today we're gonna finish up with regression, I hope. We're gonna do nonlinear regression, but remember last time we learned a very powerful tool on how to do arbitrary linear regression. So you have a linear regression model, and remember we defined linear regression by saying linear regression is any regression model where the parameters show up linearly, okay? Now the other meaning of that is that the normal equations are a system of linear equations, all right? And we learned about this regression matrix A, which was much easier to work with rather than having to define the sum of the squares of the errors and then differentiate that with respect to the parameters. We came up with this regression matrix A. It just contains the basis functions and the observations, and you just multiply it by the transpose, and boom, you get the normal equations. But still, in Python, we had to define the model function and then input the basis functions individually to build that coefficient matrix A. One might ask, though, just like with polyfit, we were able to do polynomial regression, straight line, quadratic, cubic, etc. Is there an equivalent in Python, an equivalent built-in routine that would do regression with arbitrary basis functions? Okay, thinking of linear. Okay, so that you only define the model function, your model, okay, like we did last time, whatever, 1 over a over x plus b log x, etc. Turns out, yes, there is. And it comes from the scipy library, and it's through scipy.optimize, and it's called curve fit. Curve fit is a general regression fitting routine, okay? It has a lot of features. We're only gonna be scratching the surface today. But the least number of parameters that you need to run curve fit are those three: model, xi, and yi. Now, xi and yi are your input data, your input independent variable for xi, and your input dependent variable. So those would be the arrays that you're given, the arrays of data that you're trying to fit. Your model is the name of a Python routine that implements the model function that you're trying to fit. That model function needs to have a specific signature in that the first argument for the model routine, subroutine, is always the independent variable, x, and then followed by all the parameters that are needed for the model. You could have 10 parameters in that model, or 5, or 3. It doesn't matter. Curve fit is going to figure out how to do regression with the basis functions in that model. You don't have to provide curve fit with anything, okay? Just provide it with the name of the routine that implements your model. Now, by default, curve fit returns two quantities, popt and pcov. This is a common nomenclature used in the regression community. Popt are the optimum parameters. So p parameter opt, so popt, optimized parameters. These are the parameters that minimize the square of the error, okay? So those would be the coefficients of your model. Now, the order of those coefficients is going to be the same order that you put in your subroutine. Model x, let's say a, b, c, then this is going to return a, b, c. Okay, the optimum parameters. If you put them C, D, A, or whatever, it's going to return them in that order, okay? Pcov, that's something you're not going to care about. This is the covariance of the parameter. We're not going to talk about that. You just have to put it in there so that you can separate the coefficients from the covariance matrix, okay? So all we're going to be caring about are popt, all right? So now we're going to use curve fit to redo the two problems we did last time. So if you still have those Jupyter notebooks, which I asked you to keep with you, so go ahead and bring them up. We're going to start with the first problem. If you remember, it was the disease-carrying organism decay, exponential decay. We had a three-parameter regression model. Okay? And with this curve fit, all we need to do now is just pass the name of that routine for the name of that routine that implements the model function. Okay? All right, so I'll let you grab your Jupyter notebooks. Okay. If you missed class last Tuesday, perhaps one of your colleagues could send you a copy of their Jupyter notebook. All right. If you remember, we had this Jupyter notebook over here. So we had these data. It was p as a function of time in hours, and we plotted those data, etc. And then we did the ATA, the regression matrix A. And then we did this. We printed the solution, and that gave us our coefficients A, B, and C. And then we implemented this model so that we can plot it, right? So now this is the model that I'm going to pass to curve fit, okay? So, right, so we execute all the way here. We computed the R squared, etc. All right, so now let's go and use curve fit. To do that, I'm going to import from scipy.optimize import curve fit. Okay? Now go down to the bottom. We're going to do curve fit. Now, with curve fit, if you look at the function signature, those three non-optional parameters, the name of your model function, your x data, and your y data. For my model function, all I have to pass is model, which is what we called this subroutine over here, model. Okay? And then our xi data was ti, and our yi data was pi. Okay? And I'm going to save this in popt and pcov. Okay? Then I'm going to print popt. Look at that. If you look at the results we obtained from the regression matrix, we had 4, 2.9, and 1.5. Same thing here, 4, 2.9, 1.5. In fact, the numbers are identical. Look at that. All the way to, well, except for this one, this first one here. But the numbers are, indistinguishable. Okay? So no need to even build that regression matrix A. No need to do that transpose. No need to do the lin algebra solve. You just pass that model subroutine, the name of it, to the curve fit. Okay? And again, be careful. It's going to return the parameters in the order that they show up over here, in this order. Okay? So the meaning of A, this first argument here corresponds to this first argument here, okay? And that's it. That's curve fit. Love.
Can you just go back up to the import?
Yeah, scipy.optimize import curve fit. Now, curve fit is actually doing full nonlinear regression. Although this is a linear regression model, okay, it's a special case of nonlinear regression. So inside curve fit, there's a Newton solver that solves a system of nonlinear equations. But if those nonlinear equations happen to be linear, like we had in the bonus problem, it will get it in one iteration, okay, that Newton solver. All right? Okay. So now we can do the other, oops, this one always moves over here. Let me see, left. So position on screen to the right. Okay. Now we can do the other one as well, the other problem. Can do the other problem. 1 second. Okay. Window. Okay, so this was the other problem. Okay, this was the ionic product in water, if you remember. It was temperature, it was the kWi or log kWi minus log 10 kWi versus temperature in Celsius, right? So if we do import scipy.optimize from scipy.optimize import curve fit. Why do I not import all of scipy or scipy.optimize? Because it's going to put a huge memory load if you import everything from a library, okay? So it's usually a little more efficient when you only import the things that you really need, okay? Import curve fit. So let's execute this thing over here. Again, remember we had, this model had 4 parameters, A, B, C, and D, okay? And they were like 5.2 10 to the 3, and then 1.13.4, and then 5.6 10 to the minus 3, and then minus 38.3, okay? So curve fit should give us the same answer, but all you need is this. So if you were to be using curve fit, you don't need this guy, you don't need that guy, you don't need that guy. You just need this for curve fit, okay? So let's go ahead and do it. So curve fit, and I'm gonna, what did we call it? Unimaginatively, we called it model. Model, yeah. TI. I'm the one who named it. KWI underscore popped pcov. So P optimized and P covariance. And then if we print P optimized, and if we print sol, which was our previous solution, look at that. They're almost identical, okay? Yeah, you need to do your y data needs to be minus KWI underscore. If you followed my nomenclature last time.
I didn't follow exactly, but I put in the same thing that I did.
Yeah, the minus log 10, yeah. It did not work.
Which means I might just have some of my numbers in wrong. But I just copied this from the top, and then there's my
KW2,
I just called it that, and that's why I put it in there.
and then
That's
it
not
gave
quite
you
right.
the different T3. Okay, we can look at it after class, okay? Yeah, so maybe double check, Lev. So 273, then double check the numbers. 273, 283. Oh, still last time didn't even give you the right number.
No, I couldn't get it.
A over T plus C log 10 T.
It was struggling, and I do not know why.
Plus T. Yeah, probably a typo in the code somewhere. Maybe try to restart the kernel. Yeah. Okay. Curve fit. All right. Now the hint that I gave you here is that curve fit also works for nonlinear regression. Okay, which is what we're going to do next. All right. We ready for nonlinear regression? Okay. Nonlinear regression, as the title designates. Okay. So what makes a regression model linear? And we've defined that earlier. We're going to redefine it here or restate it and put another meaning to it. A regression model is linear if the model parameters show up linearly. So again, in this class, this is the nomenclature used in this class. You might go and tell one of your other teachers, oh, this is linear regression. They'll tell you, no, this is not linear regression. It has sines and cosines. Tell them what I mean by linear regression is that the normal equations are linear. And then they'll ask you what are the normal equations. Then, because you're learning regression from the ground up, you'll be able to explain that. Okay, a regression model is linear if the model parameters show up linearly. This also implies that the normal equations are linear in the model parameters. But it also implies the opposite. If the parameters show up non-linearly, Or if the normal equations are nonlinear, then you have nonlinear regression. But you can tell from the model directly whether a model is going to result in linear regression or nonlinear regression. All right, here I have a bunch of models in the first column. The parameters are shown in red. Those are the unknowns that you're trying to optimize so that you can fit the data. And X and Y data are given to you, as usual. Okay, I want you to take a moment now and indicate which model is going to result in linear regression and which model is going to result in nonlinear regression. Okay, so which model do the parameters show up linearly and which model they show up nonlinearly? I'll give you a hint. It's okay to call A squared, for example, capital A. Okay, that's okay, right? So, for example, I'll give you, let's say, the third one, sine A x plus b. It's okay to call sine A capital A. Okay, it's okay to do that. All right. So go ahead and go through each one. Yeah, because it's a coefficient. It's yeah, it's not sine A x, right? Sine A is one of the parameters. So call it alpha, solve for alpha, and then obtain A, right? Yeah. So you don't need any transformation. Okay, you just need to call it, give it a different name. Okay. Sine A times x. Okay, sine AX, yeah, right? Yeah, so, yep, e to the alpha, yep. Because any number can be expressed in terms of any other like function, really, right? So. Which one? Mm-hmm. No, you're right. It's not. I remember you guys had the same discussion when we were doing polynomials with polynomial interpolants. Yeah. So we're not applying. Okay, let me make one more statement. We're not applying any transformation. It's okay though to rename something. Like I said, like sine A, it's okay to call it capital A. You're not doing any transformation there. But you cannot apply a log or an exponential to transform the model. Okay, with this is just looking at the model. Is it linear or not? All right, let's start. First model, linear. Okay, linear, I agree. Second model, linear. Although 1 over x is highly nonlinear, but doesn't matter. That's input data. We don't care about 1 over x. It is linear in A and B. All right, model 3. Linear. Why? Because you can call sine A, just capital A, solve for that, and then extract this little a. Okay? Okay, what about the fourth model? Nonlinear. That's right, because A is married to X. You can't separate them. All right? Okay. What about, pretend you didn't see that. What about AX parentheses squared plus B? It's linear. Yep, because you can get A squared out and call that capital A. Okay? What about X to the A plus B? Nonlinear. Okay. What about A to the X plus B? Still nonlinear. What about e to the alpha, all times x plus beta x squared? Linear, because e to the alpha, just call it capital A. What about beta e to the alpha x? Nonlinear. No, because then it becomes e to the alpha to the power x, right? Okay. All right, so now, okay, we didn't do any transformation, and some of you might be saying, well, Professor Saad, if we apply a logarithm here, we can split this up. We're not doing that in this exercise. We're going to do that a little bit later, okay? But you can do that. Okay. Nonlinear least squares regression. Do we know how to do it? Absolutely. All we have to do is define the sum of the squares S and then differentiate it with respect to the parameters. It's just the difference that so far we were dealing with linear regression models, but in general you're going to be dealing with nonlinear regression models. So if you know how to differentiate, you can derive the normal equations for nonlinear regression. And in general, if you have a model that has n parameters, a1 to ak, whatever, kth parameter, then you just differentiate your S with respect to all of those parameters, set it equal to 0, and those are your normal equations. All right, let me give you an example. So suppose you're trying to fit this nonlinear model, alpha e to the beta x, and again, in red are the parameters that we're trying to optimize. Then your summation of the summation of the square of the errors is sum of yi, your input data, minus alpha e to the beta xi, input data as well. Now be careful in your homework or in the exam. Don't write alpha e to the beta x, beta xi, because these are input data. You're doing a summation over all of those points. Now you differentiate. You're differentiating with respect to what? Alpha and beta. ds by d alpha equals 0 and ds by d beta equals 0. Those are the conditions for this squares regression. Okay? And then you do the differentiation. It's very annoying for nonlinear cases. Okay? But it's doable. Now, these are two equations that govern alpha and beta. Okay? And they are nonlinear. They are generally nonlinear. And what do we do when we have nonlinear systems of equations? We write them in residual form, which they're already in residual form, right? All I did was simplify the 2 over here. And this is a system of 2 nonlinear equations with 2 unknowns. Do we know how to solve that? Absolutely. We did that in nonlinear solvers, right? So you see how we're building up all the tools to get to do very useful things. It's 2 nonlinear equations with 2 unknowns. Okay, so let's do actually an exercise together, all right? And derive the normal equations and solve them with both, so do nonlinear regression both with curve fit and using fsolve. So for these 2 equations, you're going to need fsolve. You need to implement those as residual functions like we did before, pass them on to fsolve, and then obtain the roots. Okay? Here's a useful problem for that. The following model is frequently used in environmental engineering to parameterize the effect of temperature, T in Celsius, on biochemical reaction rates, K, which are given like a rate per day, okay? So that model, K, is given as K20 times theta to the power T minus 20, all right? K20 and theta are the parameters in this case, all right? So this is a nonlinear regression model. So you're given T and K data, okay, and you are to find K20 and theta. So this is the T and K data, all right? We want to use nonlinear regression to estimate the reaction rate at T equals 17, all right? First, we're going to use curve fit, and then we're going to derive the system of nonlinear equations or the normal equations for this model, and then solve it using fsolve, all right? We ready? Let's get new notebooks up and running, and we'll start from scratch. Actually, copy the boilerplate from another notebook. Okay, so we're going to need all of those right now. Okay, so I'm going to copy, and all right, so I'm going to import all of this, and I'm not following my own advice here. I typically would name the notebook, put my name on it, put comments, etc. But in the interest of time, I'm not doing that, okay? Biochemical, chemical reactions, example. Okay? All right, so let's import these guys first. Next, let's put in the data. So I have the data here in front of me. So ti is numpy.array. And we have 6, 12. Let me put 6.0, 12.0, 18.0, and 24.0, and 30.0. So this is temperature in Celsius. Okay? And then ki is equal to numpy.array. We got 0.14, 0.2, 0.31, 0.46, and 0.69. Okay? Let you catch up. Reaction rate per day. Okay? Give you a minute. Okay, so we're going to use curve fit first, all right? Or actually, before we do that, I want to plot the data. Let's plot the data. plt.plot. On the x-axis, I want ti, and on the y-axis, I want ki, and I want to do a scatter. Name ti is not defined. All right, now it's defined. Okay? Right? So it's a type of an exponential growth. So hence the justification of using some constant to the power t minus something. Okay. All right. So for curve fit, we only need to define the model, a model subroutine. Okay. Let's zoom in a little bit. So define. What's a good name? Model. Okay. Now, always for curve fit, the first argument in your model is going to be your independent variable. So I'm just going to call it t, okay? And then my two arguments, k20 and theta. Okay? And that model is going to return k20 times theta to the power t minus 20. Backslash theta, yeah. Yeah, any Greek letter, backslash type, and then press tab. Sorry, yeah, press tab to complete it, okay? Or put, just spell it out, theta, yeah. Okay. All right, so P optimized, P covariance is equal to curve fit. All right, are you guys in sync? Right. Curve fit, we're going to give it the model, and then the TI data and the KI data. And I'm going to print P optimized. And look at that. It found those two parameters. K20 is 0.35, and theta is 1.06. All right? So now let's plot it on top of the original data. I always like to plot the model over a range of points, okay? Not just the points that are given to us. More points in between those 2 points. So we do a linspace, okay? I call it T range, let's say, mp.linspace from min ti to max ti. So I'm putting a linspace 50 points by default between the minimum value of ti and the maximum value of ti. And then I'm going to plot my model using all of those points. plt.plot. I'm going to put t range. And then model, we're going to give it t range. And guess what? We're going to use the trick we used last time. We're going to pass star p opt. Okay, so that we don't pass p opt 0 and p opt 1 for the coefficients. So we do star p opt. And we're going to give it k dash dot. Right, look at that. Near perfect regression. Okay, and we can calculate the r squared, etc. Right? Yes. Yeah. Sorry. Sorry, I'm probably going faster than you guys are typing. Is this good? Yeah.
Wait, what did you say the star was again?
Dereferencing. You mean just the star p opt?
Yeah.
Yeah, so you got to close the parenthesis for mod. Yeah, no. You got to plot model. You're plotting the model versus t range, right? So yeah, you need model, and you give it, what does the model take? T range, and then the coefficients.
Okay.
Yeah, so you're plotting f of x, right? T range, comma, and then the coefficients, right? Yeah, there you go.
But what does the star do?
So instead of having to pass, if you were to call, so p opt contains k20 and theta, right?
Yeah.
So if you were to just pass them individually, you would have to put model, parentheses, t range, comma, p opt 0, comma, p opt 1.
Okay.
Right? Star p opt allows you to circumvent that. It just passes the entire, those two values, yeah, and substitutes them. It's very useful when you have more than two parameters, when you have like 50 parameters and you're solving it with curve fit, so you just do star p opt. Okay? All right. Did we all get this? Curve, plot, etc. Okay. Anyone?
Can I check my data?
Oh, sure. Yes. All right, it's hard to keep everything on the. And you can see the data on the PDF slides also on the Canvas page. You're still having trouble? Okay. Were you able to get this plot? Yeah. Perfect. All right. So now I want to obtain. All right. Where's my cursor? Okay. Now I want to do this using fsolve. So in other words, I want to solve the normal equations, which I know in this case are going to be non-linear. Now the first step is to derive those nonlinear equations. So this is our regression model. K20 times theta to the power t minus 20. And in red, I'm showing the parameters that we're trying to fit. Okay? Then you define the sum of the squares. That's the first step. S is sum of, just automatically, just put sum of yi or ki, whatever your input y data is. Just put yi minus your model evaluated at ti, okay, or evaluated at xi squared. Then S is minimum if its derivative with respect to each of the parameters is equal to 0. So S is minimum if ds by dk20 is 0 and ds by d theta is 0. Okay? Now here goes a tedious differentiation, and I'm giving you the answer here. Try to do the work at home. It probably takes about 5 minutes to figure out, but these are the nonlinear equations that we need to solve to obtain k20 and theta. So curve fit is doing all of that heavy lifting for you. Without even knowing the normal equations, it's doing auto differentiation internally. Okay? If we were to do that ourselves, we would need to use fsolve, but we would need to implement these two residual functions. They are two residual functions. We would need to implement them as a routine in Python, pass them to fsolve, and we would need initial conditions as well for fsolve so that we're able to solve it. So let's see what happens. Okay. I'm probably going to have to put the slides. Let me see if I can move it over there. Nope, it's not moving over there. Oh, it's like right there at the edge. Ah. It's so annoying because I cannot see it on the other screen either. Okay. So if you remember, you probably don't, but you might want to review your nonlinear notebooks and nonlinear lectures. And then once you can, you should still have that memory muscle, I hope, and then it will just become obvious. So we're going to define a residuals function. And if you remember when we discussed nonlinear equations, when you're defining a residual functions, a set of residuals, the residual functions, you assume that your argument that's coming in, you assume that you have access to the whatever you're solving for, okay? In this case, it's going to be an array that contains k20 and theta, all right? So I'm going to call them here params. Okay, those are the parameters that we're solving for. Now, by default, I'm going to make k20 to be the first parameter. You can change that. It doesn't matter, okay? You can make k20 the parameter 1 and theta param 0. It doesn't matter. But as long as you're consistent in your implementation. Now, my first residual function is this one. Theta to the ti minus 20 times ki minus k20 theta to the ti summation, okay? So all of this under summation. So I'm going to add the summation at the end, but first I'm going to put the argument. So what we have is theta to the power ti minus 20. So I'm going to do power, theta of ti minus 20, okay, times ki minus k20 times theta times pow of theta to the power ti minus 20. Close parentheses. Sorry, it's just getting all crowded over here. Let me see. All right, this is better. Okay. So this is theta to the power ti minus 20 multiplied by ki minus k20 times theta to the power ti minus 20. Okay, close parentheses. Now, all of this needs to be in a sum. Do we do a for loop? No, we do an numpy.sum, right? Because these are all numpy arrays. So we're just going to do numpy.sum. So np.sum of all of this. We're just going to sum them all up. Okay? This is my first residual function. My second one is going to be similar to the first one. So I'm going to copy and paste it. But I have here ti minus 20 times k20 times theta to the power ti minus 21. Okay? So we're going to have a ti minus 20 times k20 times theta to the power ti minus 21. Okay? Now, where does that 21 come from? It comes from the derivative with respect to theta.
So why exactly the reason there's 20 in this?
Pardon me?
Why exactly the reason 20?
That's the model that I got from some environmental engineering.
Okay,
Yeah. Why there's a 20?
yeah.
It's a model. Okay? Yes?
So why are we using this params instead of like the vars? Like we
Vars, call it vars. It's a name.
oh, okay.
Yeah, I called it params because now I'm working with the context of regression model parameters, right? So to enforce that idea, okay? Okay. If you want me to be less descriptive, I can be less descriptive. But I'm trying to be descriptive. I cannot come up with good names. Oh, man. This is probably the best name I've come up with in this entire exercise. Okay, so then we're going to return an numpy.array like we did before that contains the first residual and the second residual. Okay? Oops. Oh, no, don't leave page. Stay on page. Okay. All right. So now we have to call fsolve. So again, I need it from scipy.optimize. So I'll import curvefit and also fsolve. Okay? Fsolve. Right? Are you guys in sync? Okay. So let's call fsolve. Fsolve residuals. That's my residual function. We need an initial guess. And this is where we really have no clue what to do. And that's the challenge with nonlinear regression, because you need an initial guess. Maybe try a bunch, and I really don't know. Curve fit, the default initial guess for curve fit is 1. Okay? But you'll see cases where curve fit fails and fails and fails. And so fsolve in this case. Now, this problem has 2 parameters. So I could plot that surface S, okay? I could plot it versus theta and K20 and see where the minimum is, right? And pick that. But that's it. For 3, 4, 10, 100,000 parameters, what do you do? Okay? How do you do it? Pardon me? We're solving for the minimum of that S. So if you plot S versus the 2 parameters and look for that minimum, then you can figure out what those parameters are. So, all right, maybe we start with 0, right? Is that what you suggested, Miles? Start 0 and 0. Oh, it crashed miserably. It did not work, okay? That's great. It didn't work because it's hard. So let's try what curve fit uses, 1 and 1. Oh, look at that. It found it, 0.35, 1.069. Now remember, that's what we obtained from popt. Okay, so print popt. They're identical because curve fit is doing exactly an fsolve or a version of fsolve internally. Okay? Yes?
Is there an import for fsolve?
Yeah, so from scipy.optimize, import curve fit, comma, fsolve.
Can you show it?
Yeah, so scroll up to the top where you import. Oh, you're having it all in one notebook. So from scipy.optimize, import fsolve. Let me show it. I highly advise you guys to separate your notebooks. Don't do a master notebook for the simple reason that if that notebook gets corrupted, you lose all that you've worked on, okay?
You are too late to say this now.
So yeah, this is fsolve. So from scipy.optimize, import fsolve, okay? Now this is to show you that, yeah, we can do this, and this is what curve fit is doing. It's not doing anything magical. So in the slides, I also give you another example with this model, a times x to the power p. Make sure you're able to do the derivatives and get these answers, okay? Work through those, all right? The last chapter, the last section, is going to be what we call linear regression of a nonlinear model. Okay, guys, last section in regression, and it's called linear regression of nonlinear models, right? So, as some of you might have observed, some of the nonlinear models that we showed in that table, if you apply, like at least for the exponential one, if you apply a logarithm to it, you'll actually can rip out those coefficients from the independent variable and from the exponential. So some models that are nonlinear, very few of them, you can count them on your fingers, 2 or 3, you can actually linearize them and then solve the linear regression problem, okay? Again, with the linear regression problem, you're not worried about finding initial guesses, etc. You'll always get a solution, okay? And this is the procedure, okay? So sometimes it's possible to linearize nonlinear models by doing appropriate transformations. So here's an example. If you have something like alpha e to the beta f of x could be x squared, it doesn't matter because that's input data. What you're worried about are alpha and beta. This is a classic model in kinetics, for example. Reaction rates are obtained by this, what's called the Arrhenius rate. It's some pre-exponential factor e to the minus exponential to the minus activation energy over RT, gas constant and temperature, okay? So what you do in this case, if you take the logarithm of your model, log y model, and that logarithm acts on the exponential alpha e to the beta, it trips it out. So it becomes log alpha plus beta times f of x. Now, all you have to do is reassign or assign new names to those coefficients. So If you call log of y model, that's a totally computable quantity because your input data is going to be given to you. Just simply take the log of it. So you call that your new y model, capital Y. Log alpha, call it A naught, and beta, call it A1. And then this whole f of x, call it capital X. Okay? Then you have a linear regression model. So you've transformed your original data or your original model to a linear model, but you also have to transform the input data. In this case, the input y data has been, you acted on it with a logarithm, and this entire f of x, which in this case, for example, over there, it's -1 over RT, you call that your new independent variable. And with this, you can do a regression, linear regression on this one, which is just a straight line. Couldn't be easier. Okay? You obtain A naught and A1, and then you go back to alpha and beta. Because A naught is log alpha, so alpha is exponential of A naught. A1 is beta, so beta is A1. Okay? All right, here's an example. Here's an actual example with some data. You have a reaction rate over here versus temperature. Okay? Temperature given in Kelvin. And we're trying to fit this model for the reaction rate, A exponential to the minus EA over RT. We're trying to find A and EA. A is called the pre-exponential factor. EA is called the activation energy. T is temperature. R is gas constant, etc. Okay? So we'll do this. We'll take the logarithm of this. Log K is log A minus EA times 1 over RT. And then we're going to call this is our new model, capital Y. So we're going to be working with this new data, capital Y, which is log of K. Log A is C naught, and then -1 over RT is X, or maybe minus EA is C1, whatever, however you want to do that, it doesn't matter. And then you do the regression on this new model. All right, so let's go ahead and do this in Python. All right. Open up a new notebook, and we can do this with polyfit, actually. We don't even need curve fit. We can do this with polyfit. Okay, simple regression to a straight line. So let's see. I'm going to create a new notebook here. And I'm going to import all of these. Okay. So for the temperature, now again, for all of those models, you must compute the R-squared value. We haven't done that because we kind of know it's a given. We're trying to learn new things, and by plotting it gives us a good idea of how good the fit is. But you should never do a regression without computing the R-squared. Okay, keep that in mind. Even if it's not asked of you, like somebody tells you describe the data, do the R-squared. It tells you how good the data is, okay? All right. Oops. Stay on page. Okay, so let me grab the data over here. All right, so what do we have for the data? Pardon me. So we have for temperature, I'm going to call it Ti is equal MP dot array. And we have 313 and 319, 323, 328, and then 333. I feel like it's too bright. Let me just dim it a little bit. I wasn't able to see very well when I was standing in the back. Is this better, you guys? Yeah? Turns out there was someone who was changing the settings in these projectors every time. So they sent out, I don't know, the registrar sent out a university, a teacher-wide email for those teachers teaching in this class, like, stop messing with the projector. And then Ki is mp.array. I'm going to do 0.00043. And then 0.00103, and then 0.00180, then 0.00355, then 0.00717. Did I get that right? Okay.
You're the one giving us the data.
No, did I type in the values I was reciting?
Yeah.
Yeah. But you're correct, Miles. I'm TIKIO. Okay. This is the data. Indeed, it is exponential in nature. So a suitable model is indeed an exponential model. The challenge you will find when working and doing research is you obtain data and you ask yourself, what is the model form that I need to choose to fit those data? Okay? Many times it's just exponential or a quadratic. They're easy to find. But some other times it's more complicated, and that's where insight and looking into the literature would help you. Okay? All right. So now I want to transform this model into a form suitable for linear regression. All right. So we're going to take the logarithm. Okay. And so if you remember the slides, let me actually move the slide over to the other. Of course. Stupid. All right. Okay, so we're going to take the log of k. So we're going to call that our new y data. Okay. And minus 1 over RT, I'm going to call it my new x data. Okay. So let's declare our new xi data is minus 1 over r over t. We haven't defined r yet. And r is given to us as 8.314 joules per mole Kelvin. 8.314. Okay. So that's my new xi. And my new yi is simply np.log, natural log, of, what did I have? Ki, right? Oops, and I made a mistake here. This should be ti. So that's my new x data. Now, according to what we know so far, the data is indeed an exponential form. So taking the log from the formula is going to make it linear. So the transformed data, if we plot it, it should look almost linear. Okay? So let's plot our new y and xi data. plt.plot xi yi and give it symbol O. Look at that. Perfect line. Thank you. Okay? So this is good. This is really good. Okay. So now we can do a polyfit. Right? We can do a polyfit because polyfit, so np dot polyfit. Okay, so for polyfit, all we need are the x and y data. Now, polyfit can do interpolation or regression. In this case, we have more data points than the degree of the polynomial, because we're doing a polynomial of degree 1, which is a straight line. Okay. So we're going to give it the new xi data and the new yi data, and we're going to say degree equal 1. Okay. And that is going to give us the coefficients. Okay. And if you print coefs, okay, this is going to give us two numbers. What are those two numbers? They are C1 and C0. Okay? Those are the parameters of the transformed regression. They're not A and EA. Okay? Be careful. So what polyfit gave us were C1 and C0 in that order, because polyfit always starts from the highest degree coefficient. Okay? So really, note that C1 equal coefs 0 and C2 is equal C0 equal coefs 1. So now let's plot it. Define, what should we call it? Linear model. Okay, I'm going to give it x for x values. We're going to give it C1 and C0. Okay, and return C1 times x plus C0. So now I'm going to plot this new model on top of the original data. plt.plot. You can do a range here, but because it's a straight line, it doesn't matter. We're going to do xi. Actually, it does matter, but linear model of xi and star coefs. Okay. Now notice how I define my linear model so that it's consistent with coefs, because I know I'm going to pass star coefs. And star coefs is going to return C1 and C0 in that order. It's going to return the slope, intercept. If I had defined this linear model as C0, C1, it's going to mess it up. It's going to give you the wrong plot. Okay? So if we plot this, look at that. Okay?
Why exactly does it switch over C0 to C1?
The polyfit is just, that's how they do it, polyfit. It returns the coefficients from the coefficient of the highest order exponent to the lowest order.
Oh.
Yeah, that's how that function is designed. Just keep that in mind. Yeah. Okay, so now we can go back to the actual original model, which is if I want to get A, because I'm after the pre-exponential factor, and I'm wanting to get EA, right? So A is exponential of C0, right? And EA is minus C1. I had a little typo over here. Oh, actually, no. EA is C1. Okay? So pre-exponential or pre-exponential factor is mp.exponential of coefs, was it C0? So that is going to be coefs 1, right? That's C0. Or here's what we can do. We can say C0 is equal coefs 1, and C1 is equal coefs 0. So this is the pre-exponential factor is exponential of C0, and the activation energy is C1. All right. Now I'm going to define another model. Define exponential model. That's the original model. I'm going to give it x, and I'm going to give it pre-exponential factor and activation energy. And this one I'm going to return pre-exponential factor times e to the minus EA, okay, minus EA over R over T, right? So now I want to plot the original model on top of the original data. So far, we only plotted the transformed model on top of the transformed data. What we want to show in the end is that also the nonlinear model also fits the nonlinear data, the original nonlinear data. Okay? All right, so let's see how that works. So now we're going to go back to the original data way up here. Plot Ti. I'm going to create a range of temperatures, mp.linspace. Yes?
For the T, is that supposed to be TI or just T?
No, this, it actually should be X or T. Yeah. Yeah, no, this is a routine. This has nothing to do with Ti. This is a routine that evaluates, given those values, it returns a value, right? So next we're going to pass it Ti, but I don't want to design it with Ti, okay, in mind, okay? So then we create a linspace and min Ti here. That was Emily's suggestion, actually, a few weeks ago. We do the range from min Ti to max Ti with it defaults to 50 points. And then we plot Ti and exponential model versus Ti. So exponential model, now I'm going to evaluate it at Ti and with my pre-exponential factor, and with my activation energy, and it's going to crash. Oh, crap. T is not defined. What do you mean T is not? Oh. Meh. Look at that. Oh, it didn't plot it with the range. Plot it on TI. I'm going to plot it on the T range. Okay. There you go. So now we went back to the original nonlinear model. Okay? Yeah. It's good? It's all insane. It's like cheating with math. What do you call it, McKenna?
That's pretty cool.
It is pretty cool. So in your homework, you're going to be working with a nonlinear model that can be linearized, and you're going to solve it with nonlinear. You're going to compare all sorts of results. You're going to compare the R-squared values. You're going to see that for some nonlinear models, the coefficients that you obtain by solving the linear version of the model are going to be different than the coefficients you obtain by solving the nonlinear one. There's some sensitivities over there, and that's okay. All right? Have a good.
I'm just going to do.
Star, yep, or
Because they're the same, right?
no, because there's an
Well, they're in the same
exponential.
order, too. 1, 2, 1.
Yeah, yeah, but not coefs. This is right exponential of coef. Yeah.
Why didn't
Yeah.
you put this in the.
Because I want the function to be generic enough. Yeah, yeah. It's okay. You can do it however you like. You don't have to put them as arguments. It will take them. Yeah. That should do it. Okay. Now, one note on nonlinear models and nonlinear regression: it can be very, very sensitive to your initial condition, to initial gas. You might not always find a solution. What we find in practice is that there are two things that affect actually getting a nonlinear solution. Scaling the x and y values. If, for example, you're trying to run nonlinear regression on this pre-exponential factor, you're not going to get it. It's not going to converge because the coefficients are so large. If you notice the coefficients over here, so if you print pre-exponential factor, and if you print EA, you see that they're actually very large. Okay, so you'll see this in your homework assignment. In this case, if you were to run nonlinear regression or curve fit on this, you won't converge. Okay? There's also sensitivity on the data itself. So sometimes you might have data, let's say in milliseconds, for example, right? And it's very large, or in seconds, and it's very large numbers for X data, and your Y data is like order 1, and it will not convert. So what you do, you go to your X data and convert it to, say, a larger unit, like hours maybe, or centuries. Okay, so that you get them as close as possible to order 1. Like you don't have numbers like 100 or 1,000, right? You have numbers around 10 or 9 or 8 and so on. But it's very sensitive nonlinear regression. Okay, it's always preferable if you can do linear regression. It's always preferable to do that. But do expect that the coefficients you obtain from linear regression, when you transform them back to the nonlinear model, they're going to be different from those you might obtain from doing nonlinear regression directly. And you'll see this in homework 7. Okay? All right, that should be it. Thank you. We'll see you Tuesday.